What's going on, everybody? The networking guru here, and we're going to finish up domain 1.1 today by going over encryption, PKI, cardholder information, and DLP. So this is our fourth video and our full CYSA course. Like, subscribe, share with your friends, and let's go ahead and get started. So I'm going to zoom my face out of the way here. So today we're going over encryption and sensitive data protection. But when we talk about encryption, we're going to be going over what it is. First off, what is encryption? And then we're going to touch on PKI. We're going to touch on data loss prevention when it comes to sensitive data protection, and also SSL inspection. So to go over TLS SSL inspection, we're going to have to talk about what TLS is and what it does. And then go over PII and cardholder data. Now, this is kind of what I look at this as sensitive data protection is DLP is how we protect the exfiltration of our sensitive data, meaning we stop it. We stop the exfiltration. And PII and cardholder data is just some of the ways we can classify data to be stopped on our DLP systems from being exfiltrated, especially depending on the industry you work in, right? PII, that's like banking, cardholder information. That's also banking, finance. PII is really for everything. Any organization you're in, industry agnostic, you can't let PII get breached and exfiltrated. But then cardholder data, if you're processing credit card information, bank account information, debit card information, whether or not you're the data processor, data owner, wherever chain you're in, when it comes to processing that information, we want to ensure that it does not get leaked, it's not breached, and it's not exfiltrated. Let's go ahead and get started. So first, let's talk about encryption. So we're not going to deep dive. This is not a Sec Plus course. This is not us an intro to cybersecurity encryption fundamentals. For the CYSA exam as a SOC analyst, you just need to be aware of where to apply encryption, what it does for your data and your organization's data, how it protects, why we use it, and really where to place it. And then, of course, depending on your industry, like if you're in the DoD and you're under NIST guidelines and standards and the RMF and CSF frameworks, there may be a certain level of encryption that you have to adhere to, and you have to understand the why behind that. And then when it comes to doing TLS inspection, which we're about to talk about, understanding that flow of encryption for our data in transit will help you place that data inspection, device when you're doing TLS inspection. We'll get into that. But what does encryption do for us? So at its base, at the most fundamental way to describe it, is it takes plain text, human readable data and turns it into ciphertext, non-human readable data. If you see me hover my mouse over here, you can see that. Now this shows symmetric encryption, this shows asymmetric encryption, but no matter how you look at this is doing one thing. Using encryption, an encryption algorithm, and a key here, which we're going to get into, to take this plain text data or message I have and turn it into ciphertext, which is no longer readable. That is really the whole purpose of encryption. And again, if this was like a CS101 course on security and encryption, we could get into how the Romans used transpositional encryption to, change the alphabet around to send hidden messages with their messengers. It's been around for a while, using encryption as a way to deceive or a way to make a message unreadable to anyone intercepting our message. And in this case, in the modern computer networks, that's our data. So encryption ensures that even unauthorized parties that intercept data, they cannot understand it or misuse it. Now, in security operations, encryption gives us a lot of functionality, as in when we protect our data at rest and we use full disk encryption, things like BitLocker. That's good for our computers, our storage area networks, our devices. When they get stolen, it's fully encrypted and can't be, you can't log into it without the BitLocker pin. So it gives us that confidentiality for our data at rest, for our data in transit. If we have site-to-site VPNs using IPsec, that's going to be a cipher suite or an encryption standard for our VPN connections that allow us to protect our data in transit and allow our data payloads to be protected from things like a man-in-the-middle attack, or just if it's exposed in general. It gives us confidentiality on our data in transit. Encryption can actually also be used for our data in use. So you can do things like adding an NX or XN bit to your data in use, processing data from your CPU or from your RAM. We have things like address ASLR, address layer randomization. That's also kind of encryption in use that we're not going to dive into here. That gives us confidentiality at all forms of our data, whether it's at rest, in transit, or in use. We have things like authentication. So encryption, specifically asymmetric encryption, is used in creating things like digital signatures, which give us non-repudiation and allow us to have some form of authentication, so we can make sure that who's ever sending this data is actually the original sender and it wasn't intercepted. So encryption also gives us that ability. Now, the two primary types of encryption algorithms or keys is going to be symmetric and asymmetric encryption. Now, typically when I teach, we go over symmetric encryption first, and that kind of gives us the idea of what encryption does. So we look here, we have Amanda and we have Steven, our sender and our receiver. So our sender here, Amanda, she wants to encrypt this message to Steven. Now imagine, again, these are maybe geographically dispersed devices or users. So maybe Amanda's sitting at a site in Phoenix and Steven is sitting at a site in New York. So they're not local, we're not switching traffic, they're not on the same switch, they're distant. This is using an internet connection to talk to each other. So, back to the encryption. So Amanda wants to encrypt this message. So she's going to use a symmetric key algorithm or encryption standard or encryption key. So she wants to use like AES. Well, when we use AES, we have our encryption algorithm, and then we also have the key. That key is what locks and unlocks. That is what encrypts and decrypts. We need that key to be able to use this encryption algorithm to actually encrypt. Then that same key is going to be used to decrypt. So with symmetric encryption, we have one private key or one secret key that's used for encrypt and decrypt. So she's going to encrypt that message, send that encrypted message over to Steven, and then she has to figure out a way to also send that private key over to Steven so that he can use Amanda's private key to decrypt. So hopefully you kind of see just from that small example where some issues may lie in symmetric encryption. So obviously it's the transmission of that private key. Well, what if it gets intercepted? Well, how do we securely transmit it over to the receiver? And that's the problem, right? And there's solutions. We're going to talk about those solutions. Now, another question that may pop into your head, well, why? If there's this obvious vulnerability, why use symmetric encryption? Well, one, because we kind of fixed that vulnerability with the secure key exchange. Then we'll get into that. But also, symmetric encryption is less resource intensive. So for like data in transit encryption, we're doing like stream ciphers or a block cipher to encrypt our data payloads, and we're sending gigabytes at a time. Symmetric key encryption is going to be what we want to use, or symmetric encryption algorithm is going to be what we want to use. It's less resource intensive. So it's taking that, it's easier for it to do these big bulk encryptions for us. Now, how do we securely exchange that private key? That's where asymmetric comes into play. Asymmetric encryption algorithms or asymmetric cryptography, this does things a little different. With asymmetric encryption, we create key pairs. And now these key pairs are mathematically related, meaning that when I create these key pairs, whether or not I arbitrarily designate one as public or private, what I do with one, I undo with the other. Now, of course, we're going to label a key public and one private for our uses, for our, we use this asymmetric encryption for PKI, for secure key exchange. So we're going to have to put labels on both these keys, one being public, one being private, and then use it for that purpose, with the public key being exposed to the global internet, to your enterprise, and the private key being stored locally, maybe with the root user stored in a local cache, like SSH keys in your local SSH cache that has to be accessed using sudo. I'm thinking of like a Linux web server. But these two keys are mathematically related. So if I encrypt with my public key, the only thing that can decrypt it is my private key. So guess what? If I encrypt with my private key, what is the only thing that can decrypt? You guessed it, my public key. So two mathematically related keys. Now let's take a look at this example here. Let's say we have the same scenario. Amanda wants to send Steven, she's the sender, Steven is the receiver, an encrypted message. So here's how asymmetric encryption would encrypt that communication. Amanda so we're in asymmetric cryptography. She'll create a public and private key pair, as will Steven. He'll create a public and private key pair as well. What she's going to do to encrypt this message is she's going to go grab Steven's public key. So imagine, again, we're in an environment. We have, maybe this is our enterprise users, and we're using PKI. So we're trying to send an email. So Steven and Amanda and all of our users publish their public keys, their certificates to the global address list, okay? Real world example. I've done this in Outlook in every enterprise I've worked in, okay? When we want to send encrypted emails. So asymmetric cryptography, back to it. Amanda's going to go grab Steven's public key. So the sender is going to grab the receiver's public key. They're going to use the receiver's public key to encrypt. And then they're going to send that message on the way. And guess what? If you encrypt with the public key, what is the only thing that can decrypt? You guessed it, the private key. So Steven's private key, which now is stored local to him, that no one else should have, it's secure, it's protected in that local device, is going to decrypt that message. That's how asymmetric cryptography works. Now you may say, well, if this key is public, isn't that vulnerable? And of course not, because guess what? If you encrypt with the public key, you can't decrypt with that key. You can only decrypt with its pair, which would be a private key that you're supposed to store locally. Now, let's get back to this. Because I told you, symmetric encryption is used for data in transit a lot of times. We use AES encryption. It's for bulk. It's more efficient when it comes to our compute resources. So how do we securely exchange that private key? Well, we have secure exchange protocols like Diffie-Hellman, elliptic curve cryptography, Diffie-Hellman elliptic curve cryptography, combinations of it. And what that does is it uses algorithms like a Diffie-Hellman algorithm, and Amanda's going to take Steven's public key and her private key, and Steven's going to take Amanda's public key and his private key, and they're going to do some mathematics. I can't get into the algorithm, like a Diffie-Hellman algorithm. And from there, they're going to create a shared private key. So we use asymmetric encryption to create a shared secret key that is only going to be available between our session, and we're going to use that secret key to then do our bulk encryption. Let me pause the video real quick. Let me go grab an image of Diffie-Hellman so I can show you what this looks like. Okay, so I found an image from our Network Plus course where I talk about this briefly. And you can see here the Diffie-Hellman key exchange. Now, this is just one way that asymmetric encryption creates a shared secret key to then be used. So we have Alice here. And what Alice is going to do is it's going to combine her private key with Bob's public key, and it's going to create this shared secret key. Bob's going to do the same thing, take his private key and Alice's public key, and it's going to create a shared secret key. And mathematically, without us diving into it, because again, I'm not trying to spend a whole semester on encryption. We just got to get through CYSA. These keys are now mathematically related. These new shared secret keys that only we would have access to in our shared session here, right? So that's how we can use asymmetric encryption cryptography to create a shared secret key with each other that would not be exposed to any man-in-the-middle attack, because someone would literally have to be in this transmission right here, which again, they're not going to because we're encrypted. So that is how we use asymmetric cryptography to create a shared secret key. And I'm going to pause the video again and get back to our CYSA slides. Okay, so now that we've gone over encryption, I think at a pretty good level, let's just again read the little note here so we can summarize it. So symmetric encryption uses a single key for both encryption and decryption. It is fast and efficient, but key distribution can be challenging since the same key must be securely shared between parties. Asymmetric encryption. This uses a pair of keys, a public key for encryption and a private key for decryption. This method underpins the most secure communications today due to its ability to solve the key distribution problem, which we talked about at length. Okay, now, we talk about encryption, and this helps us explain what we're about to go over, which is the public key infrastructure. You use this every day without probably even knowing about it, because it's baked into your web browsers. It's just baked into how the internet communicates. When I go to Google Chrome and I go to HTTPS https://whack-whack-facebook.com. That connection is secure. If I were to do a Wireshark capture on my device right now, which I will, and I try to look at my HTTP connections, try to look at the data payloads, I won't be able to see it. And that's because we're doing TLS. We're adding transport layer security onto our HTTP sessions. Now, what makes that possible? What makes it possible for my web browser here, from the client, to make a secure connection all the way to the web server, where no one in the middle can see my data payloads? It's the public key infrastructure. So the public key infrastructure is a framework, it's an architecture that allows the secure communication, authentication, and encryption globally at a large scale. You use it every day. PKI can also be used just within your enterprise. Within the DoD, we would have these tokens, these cards that were part of the PKI. It was a huge PKI system. And individually, like me, my individual user account would have that token with an X.59 certificate on it that had a public key that related to my user identity. So PKI can be used at a large scale. It provides a trusted environment for managing public and private key pairs and associating them to their digital certificates with trusted providers, and a way to have that client to server, that sender to receiver encryption. So before we dive into the components of PKI, let's go take a look at a Wireshark session, show you how the TLS is working on HTTP. I'm going to pause the video and bring up a Wireshark capture. Okay, so I'm at my Wireshark screen here. So just a little note, because I don't want people commenting like, hey, this actually is not 802.11. So I'm going to capture on my Wi-Fi. But I didn't have, in Wireshark base, it only captures 802.3 Ethernet by its standard. But I'm capturing my Wi-Fi NIC, which is transmitting 802.11 at layer 2. So the layer 2 information is simulated, it's emulated. You can capture 802.11 frames using Wireshark, but you have to do some additional plugins and configuration that I haven't done. Just want to preface that. So here's Wireshark. Here's how we can analyze network traffic. I'm going to type in HTTPS here, and I'm just going to look for HTTPS, or let's do TLS traffic, okay? So I'm going to stop it here, and let's just take a look at this one packet here. So as you can see, I am talking to whatever this IP address is, 156.4578.50. If I open up my terminal here and I zoom in so y'all can see it, I type in NSLOOKUP. So I do like some DNS lookup here, 156.45.78.50. I am talking to a server that does not have DNS resolution on. Oh, right, Zoom. So I'm talking to Zoom right now, right? I have sessions going to zoom.com on my NIC, on my internet sessions here. So I can see that. But I can't see my data payload. Why? Because of this. Because of TLS. TLS is encrypting this session from client all the way to destination, from client to server. So what enables TLS to be possible is the public key infrastructure. Now, I just wanted to quickly show you that. This is also going to help us when we get into TLS inspection. Now let's head back to our slides. So, went over the why. Now let's go over how PKI is accomplished. So PKI, the public key infrastructure, is going to have key components here. We have our certificate authority, our registration authority, digital certificates, and of course we have view, which I would call the requester. So the certificate authority is going to be that trusted entity that's going to have a chain of trust and other trusted third-party providers that our web browsers trust to issue certificates. So that certificate authority is going to issue that certificate to a web server to be able to do HTTPS. Then we have an RA, a registration authority. That's going to act as an intermediary between users and the certificate authority, handling requests and verifying identities before certificates are used. And then we have the actual digital certificates, which are going to contain our public keys. When I say our, I mean the web server that wants to do HTTPS to have those encrypted sessions for all their users. That digital certificate is going to contain our public key and a hash that's going to verify the authenticity and integrity of that certificate from the certificate authority. Okay? Now, here's a little diagram here of all the components and kind of the flow But I'm going to bring up a whiteboard and actually go over this flow with you and kind of give you the why behind it. Because I do believe it's important to understand the why when you go be that SOC analyst describing PKI, at the table when we're sandboxing things and going over things as an enterprise. Let me pause the video, bring that whiteboard up. Okay, so here's my little whiteboard diagram of PKI. Now, here is some key components we're going to talk about. So imagine you start a company, you call it trepatech.com. So you go buy your domain name, you start building your website. It's being hosted by like Bluehost or Wiz. It's a WordPress site, whatever the case may be. And now you want to make sure you have that nice little lock icon on top so users can access your website and feel protected. Because there is some digital literacy, especially amongst my generation and younger, to know what websites are safe and not safe. Even if you don't know the inner workings, the deep workings behind it, you see red, we know that equals bad. Sometimes we don't want to have a click that says, hey, this website is not secure. We don't want that because we're trying to get people's money, have them trust us. So we are going to do an SSL request. We want to activate HTTPS. So to do that, we have to do an SSL request. So we're going to do an SSL request. So that's going to look different depending on how you're doing this. Like if you're doing a Wix site, it's literally just like a little add-on. It's just like, oh, enable SSL for $3 a month or something like that. And this is what happens in the background. Now, if you're managing this Linux web server, for example, this is going to be like from the terminal, from your bash terminal, where you do that SSL request, and you're going to have to put in a bunch of information, your time zone, the domain name, things like that, okay? So during that SSL request, you're going to generate on your web server, guess what? A public key and a private key. Now, you can use like RSA as an encryption algorithm, an asymmetric encryption algorithm we can use. We have DSA, other things like that to generate these key pairs. So you generate your key pairs, public key and private key. That private key gets stored here. Then that public key during your SSL request is going to go to your CSR, your certificate signing request. You're going to put your public key in there. And in that CSR is going to be all that additional information, your domain name, your time zone, your location, all the other things that come along with that SSL request, okay? And then you're going to send that SSL request to a trusted certificate authority. Let's say that's like, I don't know, maybe Cloudflare's a certificate authority. I can't think of the major one on top of my head, GTS. So that CSR, you send it off. Its first stop along this path is going to be the registration authority. Now, that registration authority is like the bouncer at the club. Are you going to come in or you're not going to come in? Are you going to pay the fee? Well, you might have already paid it. Anyways, the RA is going to say, okay, let me verify you. Are you on a blacklisted domain name? Does this look sketchy in some way? No? Okay. I'm going to pass you off to the CA. Now, typically, this is going to go to an intermediate certificate authority. And then that intermediate certificate authority is part of that chain of trust at the root CA. And they're going to issue you a certificate. So they're going to jot down your information. Okay, trepatech.com, request a certificate. And we're going to generate what's called an X.509 certificate. So that X.509 certificate is what's going to be used for all your HTTP sessions to actually establish that TLS session. Because in that X.509 certificate, it's going to be a couple key things. One is going to be your public key. And when using your public key, yes, it's global, but that's okay. Because only your private key can decrypt that public key. So in that X.509 certificate, that's the main thing that's going to be in there, your public key. There's other things that are in here as well, like the expiration date. There's going to be an expiration date for the validity of your certificate. And that's also going to be stored, this expiration date, in something called a CRL server, a certificate revocation list, which is literally exactly what it sounds like. It's going to be a server that has a database of all certificates that maybe are expired or no longer good, whatever the case may be. In there's also going to be a digital signature. So that digital signature is really just going to be a hash of our trusted CA here that authorizes X.509 certificate, okay? And it's going to be done using, well, anyway, it's digital signature is part of it. I don't want to get too deep. And that's going to be issued to you. And now you can have that satisfying S right there. Now, you may be wondering, where do I play into all this? Well, baked into your web browser is going to be the trusted CAs. So like if you're on Google Chrome or whatever, you import it from your laptop, like your Mac OS, like, oh, the certificate authorities we trust, they're going to be baked into this web browser. And that's how this system's like bootstrapped. So all your trusted CAs are going to be baked in here, and you're going to have all those trusted CAs public keys. So when you're verifying that X.509 certificate from here, and it has that digital signature on it, you'll decrypt it, or you use a hash value, right? And you can be able to see, oh yeah, I trust that digital signature, and I trust that this certificate was truly issued from this root CA, and now I am able to use that asymmetric encryption, the public key from that certificate, to establish a TLS session here. And in that TLS cipher suite, we may have something like RSA for the asymmetric, Diffie-Hellman, and then something like CySA 20 for the symmetric encryption of our actual data. I don't want to go any deeper than that. That's the best way I can explain how PKI works at the global scale and how each component works, okay? I have another little thing here called OCSP, the Online Certificate Stapling Protocol. You can use that to reach out to see if the cert should still be trusted, if it's expired, things like that, okay? Now, let's take a look at two websites here. I'm going to bring up Google Chrome, and we're going to take a look at two websites. Okay, so here we have my Academy site. And if I come here, I see my connection is secure. My certificate is valid. And this is the X.509 certificate that lives on my web server. We see the public key there, the actual certificate and its hash. Look at the details. And I'm using this certificate authority. And here's the chain of trust. GTS root 4 is like the root CA. This is probably my intermediate CA. And here's everything else a part of my certificate. There's my public key, the actual certificate hash, the signature value, the algorithm. It was, this is the asymmetric. This is the actual hash right here. It's like elliptic curve, something algorithm. I forget what it's called. It's bad. Maybe I'll edit that out of the video. Here's my public key. The public key algorithm is elliptic curve public key. So, anyways, that's valid. And baked into Google Chrome, I trust this CA. So I trust the certificate that academy.trepatech.com is showing me. Let's say I go to this website, a .mil site. You see I'm using HTTPS. I'm able to use HTTPS. It's totally possible. But it says non-secure. My certificate's not valid. Well, why? I mean, I have a public key. I'm using SHA-256 fingerprints. It looks like everything should be good here. I have the public key, the certificate hash. Why is this not trusted? Well, that's because baked into Google Chrome, let's go back here, DoD root CA3 was the root certificate authority. That's not trusted. I do not trust that certificate authority. So automatically, I'm going to say, hey, I don't trust this connection. And that's PKI, guys. That is how it works at a global scale. Now, again, like I said, this could also be done in your enterprise as well. Now, let's go back to the slides and finish up this video before it becomes an hour long. Okay, so now before we move on, let's just go ahead and read some of this little summary here. So PKI is a framework that enables secure communication, authentication, and encryption on a large scale. It provides a trusted environment for managing public and private key pairs and their associated digital certificates. All right, let's go ahead and put a cap on that. Now, SSL, TLS inspection. We already looked at our Wireshark capture, looked at what TLS looks like. So what is inspection? So imagine you need to monitor and look at the data payloads of your users. Well, if they're accessing sites via HTTPS, you will not be able to do that because it's encrypted from end to end. And we saw that. So what can you do to actually do that deep packet inspection? You need to activate, whether that be somewhere in line, whether that be on an IDS system, on your next generation firewall where you're doing intrusion prevention, or in your activating DLP, and you want to do data loss prevention, and you want to see those web traffic that's protected with HTTPS to see if there's command and control services going on here, a C2 server exporting or exfiltrating data that you wouldn't be able to see. You want to activate TLS inspection. So imagine that almost like a device sitting right there in the middle, in line between your client and the web server session. So probably inside the enterprise, definitely inside the enterprise, maybe at a firewall. You have to decrypt that TLS session, do the inspection, and then encrypt it and send it on its way. So if you want to be able to monitor the activity of your users that are using HTTPS to do web browsing, you have to activate SSL/TLS inspection. So TLS inspection. So while SSL/TLS provides encryption, malicious activities can be hidden within encrypted traffic. That's true. Like C2 services are hidden in DNS, HTTPS all the time. So TLS inspection enables organizations to decrypt, inspect, and re-encrypt traffic to detect threats without compromising the overall security of that web traffic. Something that a lot of network engineers don't even realize sometimes when they're trying to do Wireshark, NetFlow captures, they're not getting the full picture sometimes. Okay, now moving on to sensitive data protection. Let's talk about DLP. So data loss prevention, this is technology, really a technique, right, that stops sensitive data from being exfiltrated. DLP can be installed on endpoints. This could be installed and be part of like your next generation firewall. So it could be installed in line. It could also be an additional feature, maybe on like your EDR or XDR systems, your endpoint detection response or extended detection response systems. This could be part of your antivirus, anti-malware software suite. But really, this refers to strategies and tools designed to detect, prevent, and respond to unauthorized access or transmission of sensitive data. So key components of DLP: content analysis, inspects data for patterns, keywords, or formats indicative of sensitive information. So before we use DLP effectively, we have to tell whatever DLP system that we're using, whether it's in line on the network, on an endpoint, whatever the case may be, we have to put data classification saying, look out for this. Look out for what may look like social security numbers. Look out for what may look like primary account numbers, a credit card number. Because if you don't tell it what to look out for, it's useless. So you have to classify that data. So for example, we're worried about the GDPR. We have a lot of EU users. We're doing cybersecurity in the EU. Maybe part of that DLP system is activating the GDPR data classification that says, hey, we're not just servicing American and what their PKI or sensitive banking information looks like. We have EU customers that we also have to look out for. This helps with policy enforcement, applies rules to prevent data exfiltration, such as blocking an email containing sensitive data or encrypting data being transferred. We have monitoring reporting, so we can also have a DLP system that reports like, hey, this data is being exfiltrated. Okay, now let's go over some of that data we want to protect. So PII. So personally identifiable information includes any information that can be used to uniquely identify an individual. A little redundant there. But this includes names, social security numbers, email addresses, physical addresses. Now, this could be, like a name. Like really, we don't want names being breached. It really just depends on how restrictive we want to be of PII being breached in our industries. So protection of PII is a regulatory requirement in many industries. It's required, like the GDPR, HIPAA laws. We can't have patient health information getting out. That's sometimes called PHI, but it's part of their overall PII, right? Like medical records. And then last, cardholder data. So PCI, that's the first thing that comes to mind, the Payment Card Industry Data Security Standard. We're going to have cardholder data that we don't want being exfiltrated. So examples of this is a PAN. If you see that acronym, that means primary account number. We don't want the cardholder name, the CVV, being exposed and exfiltrated. All right, so let's go ahead and do our quiz before this video becomes an hour long. Okay, so I'm at our learning management system here. If you want access to this, go to our trepatech.com, go to our sales page, and you can get access to this LMS of all the different questions and the quizzes that I'm about to do. So let's go to our CYSA course. Let's go to this lesson, domain 1.1.4, and let's go ahead and take our quiz. I'm going to zoom in here so it's a little easier to read. Okay, so question 1. Which of the following is a key feature of data loss prevention systems? So we're going to go with C, monitoring and controlling the movement of sensitive data. So that's what it is, right? We're stopping the exfiltration of sensitive data. We're monitoring that and alerting us, and also, preventing it as well, the P in DLP. Go ahead and pause the video if you'd like to read the explanation. Question 2. What is the primary purpose of encrypting cardholder data? So cardholder data, that's sensitive information that if it's being sent across the wire, across the internet, we want to encrypt it so it can't be inspected and there's no man in the middle looking at it. So what is the primary purpose of encrypting? That is to prevent unauthorized access to sensitive payment information. B, data integrity. So encryption refers to confidentiality. Remember that. Integrity means that it wasn't changed, but encrypting means confidentiality where we can't read it at all. All right. Pause the video if you'd like to read the explanation. Question 3. Which encryption protocol is the successor to Secure Sockets Layer and is widely used for secure communication on the internet? I don't know if I explicitly touched on this, but yes, SSL is what used to be used with our HTTPS web server client architecture and sessions, PKI, whatever. That's older. It's insecure now. If you're using SSL, most web servers won't even allow you to. Like they enforce, through HTTP headers, they'll enforce high levels of TLS, like TLS 1.2 and 1.3. Anyways, TLS is the secure version, okay? Pause the video if you'd like to read the explanation. Question 4. Why is TLS inspection an important feature in modern security operations? So it's going to be B. It allows organizations to detect threats hidden in encrypted traffic. Question 5. Which of the following best describes the role of public key infrastructure in security operations? So obviously I went deep into this, but a quick answer is going to be B. Managing public-private key pairs and digital certificates. And that's what it does. And that gives us the ability to have these secure web sessions globally or to have secure sessions within our enterprise. Pause the video if you'd like to read the explanation. Question 6. What type of data is considered personally identifiable information, PII? So this one's kind of easy. Social security number and email addresses. Something that can identify you. Something that's unique to you. Pause the video if you'd like to read the explanation. All right, we got that 100%. Let's go, people. So I want to thank everyone for viewing. Make sure you share this with your friends. If you're watching this on YouTube, like and subscribe. If you're watching this on Udemy, thank you for the support. If you're watching this from our LMS, thank you for the support. We hope you enjoy those additional features. Stay tuned as we finally move on to Domain 1.2.